All right, so problem 20. So we have a hot industrial wastewater at 15 bar, 180 degrees Celsius with a mass flow rate of 5 kilograms per second. So that's coming in at state one, enters a flash chamber via a valve. And so what I'm going to do, I'm going to put, I'm going to change the numbering, I think, here. So what I'm going to do is I'm going to say this is state one. Let's say this is state two. This is state three. Okay, fine. That could be three. This could be four. And let's call this five. Okay, perfect. All right. So you'll see why it was labeled like that before, and it'll make a little bit more sense, but I don't want to cause any confusion. So we've got things coming in at one, going through a valve, and then it enters this flash chamber. So the job of the flash chamber is to separate two phases. So what comes in at state two is saturated, which means that it's got two phases. Part of it's a saturated liquid, part of it's a saturated vapor. And the flash chamber, this box here, is going to separate those two phases, right? So the saturated liquid portion is going to come out at state three, and the saturated vapor portion is coming out at state two. That's all it does, okay? And the problem statement gives us basically the information that we need to fix state two and fix state four. That's going to be confusing, and state three. All right, and then the saturated vapor portion passes through a turbine. So what we need to do is we need to figure out the power required, or power generated, I should say, not required, because this turbine is a work producing process. We need to get W dot for our power output. Okay, so put a little W dot because that's where it's occurring. And just keep in mind, what does our first law and our conservation of mass tell us? So our conservation of mass, write it right here, dmdt equals, I've got Q dot minus W, oops, I'm sorry, that's my conservation of energy, isn't it? So it's going to be my sum of the m dots coming in equals sum of the m dots going out. And I think I want to make that a little bit thicker there. And if it's steady state, dmdt is equal to 0. And so all it's going to give us is that the sum of my m dots coming in equals the sum of my m dots going out. Okay, so that's going to be for any system that I look at, any control volume that I choose to analyze. All right, and we're going to analyze multiple control volumes, so just keep that in mind. All right, but all of them are going to be evaluated at steady state, which is why I got rid of that dmdt. My conservation of energy, let's go ahead and put him over here. So I got dE dt equals dot minus W dot plus, got the sum of the M dot H's plus kinetic and potential. And I know that, normally we would write the velocity squared over 2 and the gz for potential energy, but I'm going to end up canceling those things out because it does tell us in the problem statement that kinetic energy and potential energy effects are negligible. So I've got that right there. All right, but back to my first law. Perfect. So I will go ahead and cross this out because everything is operating at steady state. Again, I'm not specifying which control volume I'm going to look at yet. I'm just saying that particular, for all of these devices, they're going to be analyzed at steady state. I may have a power output, right? For my turbine, I do, so I won't cross that out. It does tell me that in the problem statement, it says stray heat transfer can be ignored. And so I'm going to go ahead and say, well, it doesn't matter which control volume that I happen to be looking at, dot's going to be 0. Okay. And then, of course, kinetic and potential energy changes are going to be negligible. So W dot is going to be sum of the M dot H's going out minus the sum of my M dot H's going in. Perfect. So if I don't happen to have a power input or output, for example, if I analyze this flash chamber, well, I wouldn't have a W dot. We'll see that in just a second. So I'm just kind of simplifying as much as I can to be applicable to as many control volumes as I can. All right. So, well, let's go ahead. If I apply, I know this is my conservation of mass, my conservation of energy. As far as I can get it simplified down for whatever control volume that I happen to be looking at. Again, that power could be going away if I'm looking at the flash chamber, for example, but we'll see in just a second. So, but if I apply my first law to my turbine, let's do that. So my turbine is right here. I have one inlet, one outlet. So, M dot 4 and 5 are the same. In fact, let me go ahead and I'll put in parentheses that my conservation of mass tells me the sum of the M dots coming in is equal to the sum of the M dots going out. So I'm going to say, I'm going to say M dot 4 is equal to M dot 5. I'm just going to kind of put a pin in that, right? But my first law is going to tell me that W dot, and I do have a W dot, my W dot is equal to sum of my M dot H's going out minus the sum of my M dot H's going in. Perfect. Right. So, like there was, yep, that's perfect. All right. So I know that this is going to be equal to M dot 4. I'm just going to call them M dot 4, not M dot 5, but well, I'll simplify it in a second. So going out, I've got things going out at 5 and things coming in at 4. And I'm just going to simplify that and call that M dot 4 times H5 minus H4, right? So that's my governing equation, right? That's my governing equation. I'm going to put that, kind of highlight that there. This is my W dot. And let's put a little highlight right there. Very excited about that. Perfect. All right. So let's see what information I can get here. I can get those enthalpies, I think. Yeah, because I've got two independent intensive properties at 4 and 5. So at 5, if I kind of zoom in here, well, it's obvious what properties I have at 5. It's pressure and it's quality. They've given it to me. And so all I need to do is look at my saturated tables that are organized by pressure. So that's table A3, water. And I would just need to calculate H5. It's going to be my H sub F plus my quality times my H sub F. So I will leave it up to you to plug that guy in and see what that is, but perfect. Actually, I'll go ahead and write it down. So my H5 is going to be 173.88 plus my quality, which they gave me as 0.9 times my H sub FG, which is H sub G minus H sub F. Got 5, oops, what was that? 2577 minus 173.88. And all of this is going to be, there we go. kilojoules per gram. All right, perfect. So I got that guy. I'm going to kind of circle him. Got state 5. Ooh, I don't have them because I didn't give you a number yet. So I've got 2336.669, or actually just 69. 2336.69. That guy is kilojoules per kilogram. Perfect. All right. There's H5. Let's go see what H4 is. So H4, they give me that is a saturated vapor, which means, that's fine, delete him, which means that my quality here is going to be 1. So when I look up in table A3, when I look up what my H value is, it's going to be the H sub G value. So, right, so my H4 is going to be H sub G at P4. And I end up getting, let's see what I've got. 2738.6. 2786. And this is going to be kilojoules per kilogram. Perfect. All right. So I have enough information there. That's good. Let me put some check marks here. I've got this guy and I've got this guy, but what I don't have is M.4. So what I need to do is I need to kind of go back and see, all right, what's going on over here. All right, so let's do that. So I need to find M.4. All right, that's fine, no problem. So I remember, still got my conservation of mass, and I can apply that wherever I want to. I think I'm going to apply it to my flash chamber, and let's see what happens there. So if I apply my conservation of mass to my flash chamber there, then I'm going to have, write that, conservation of mass applied to my flash chamber. So that's going to give me that, all right, M.2, because that's going in, M.2 is equal to what's going out, right? Sum of the M dots going in, M.2 is equal to the sum of the M dots going out. Be M.4 plus M dot. And if you did a conservation of mass on that valve right there, you would see that, well, for the valve, by my conservation of mass, whatever is coming in, all the M dots going in, L1 is equal to the M dot going out, M.2. So this is also to M.1. All right. So at least I know that. So I know M.1, which is equal to 5 kilograms per second, for M.2 is equal to my M dot, I'm going to write these in order, M.3 plus M.4. That's good, but I still have 2 unknowns. So did the conservation of mass or conservation of energy? Again, on my flash chamber. Right? So what's going to happen is when I apply my conservation of energy, it's this up here, all this right here. So I had figured out for any of these devices, I knew that steady state, d dt goes away, q dot goes away, kinetic and potential energy goes away for anything in this whole system thing. But if I want to analyze just this flash chamber here, well, I can also get rid of that power, right? So I don't have any power. So all that first law is going to boil down to is that the sum of the m dot h's coming in equals the sum of the m dot h's going out. So let's go write that. Okay. All right. So going in, I have I have things going in. I should probably change this stuff over here because I messed up my numbering system. It's two, and then I think everything else could stay the same. Nope, that was now four. Yeah, there's four, there's three. That's fine. And then the other guy was five. Messed him up. Oh well, it's fine. Okay. All right. So sum of the m dot h is going in. That's m dot 2 h2. M dot 2 h2 equals the sum of the m dot h's going out. I've got things going out at 3 and 4. So I have m dot 3 h3 plus m dot 4 h4. All right. So I should be able to get those values, those enthalpy values. So at state 3, let's see what I have. I know I have this guy, right? I have this. I've already figured that guy out. What was he? He was, let's see, 2738.6. Yeah, 2738.6 kilojoules per kilogram. H5, we had calculated that based on our quality. That was 2336.69 kilojoules per kilogram. Now I need to figure these other guys out. So at state 3, I've got a saturated liquid, meaning that my quality is 0. So H3 is going to be the H sub F at 4 bar. And this guy is going to be found in table A3 as well. And I got a H3, see, at 4, it's at 0.8 bar. 604.74. All right. That's kilojoules per kilogram. And I know I'm going to need H2. So I have to look at H1. Remember those throttling processes. That's what this is. This is a throttling process, which means, remember, we might model those as isenthalpic, meaning our delta H is 0 across that valve, which means whatever H1 is, that's what H2 is. So if I found out what H1 is based off of the fact that it's 15 bar and 180 degrees Celsius, then I have figured out what H2 is. So I'm going to write that here. So I know that H1, same as H2, based on this pressure and temperature. What we'll find is that at that pressure and temperature, it's actually superheated. So at 15 bar and 180 degrees Celsius, actually, let's see. Is it superheated? I don't know. Let's go see. 15 bar, 180 degrees. Let's go look. Ah, maybe not actually. So in table A3, 15 bar, we're at 180 degrees. We're actually less than the saturation temperatures, at least subcool. Means I could since it's compressed, right? And I know it's compressed because my temperature is less than the saturation temperature at 15 bar. Since it's compressed, I'm going to say that my H is a little less. My H1 is approximately H sub F at T. Why am I doing that? Because it is a compressed liquid, and so we can use a compressed liquid approximation, and that's what we're doing. So it's compressed, using a compressed liquid approximation, H sub F at T. So I need to go to the saturated tables that are organized by temperature. So 180 degrees all the way down here, H sub F. So that's this column right here. So, oops, not that one. 763.22. Perfect. So this is, oops, 760.22 kilojoules per kilogram. Awesome. And so now I think I've actually got enough information to plug things in. Got all of those H values. You bring this down here so I can have it there. So I've got that M2 H2 is equal to M dot 3 H3 plus M dot 4 H4. And if I'm keeping track of what I know now, I know H2, H3, H4. I know M dot 2. M dot 4 was the thing that I needed to calculate the turbine power output. I don't know M dot 3. However, I do have my conservation of mass. And that's my other equation that I'm gonna use. So I know that the sum of the M dots coming into that flash chamber has to be equal to the sum of the M dots going out, right? So I know that this is my first law. That was what my first law told me. And my conservation of mass told me that M dot 2 is equal to M dot 3 plus M dot 4. So all I'm going to do is I'm going to rewrite this. M dot 2 H2 equals not M dot 3, but rather M dot 2 minus M dot 4 times H3 plus M dot 4 H4. All right, and so now all I'm going to do is gather some like terms. I'm going to solve for M dot 4. So let's see what I've got. So I've got M dot 4 equals M dot 2 times, and it'll be H2 minus H3 over H4. I don't know what I was doing there. Yeah. Yeah, H4 minus H3. Yep. All right, and so I've got an equation now. Now I know everything, right? M dot 2 is 5 kilograms per second. I know all the enthalpies, and so I can plug in, and I've got a mass flow rate of 0.371 kilograms per second. So with that information, now I can go back to that equation that I had before for power. So I've got power was equal to, it was M dot 4 times H4 minus H5, right? Or I'm sorry, it's out minus in, wasn't it? So it's, oh, wait. Oh, somebody was like dying over here. Look what I did. What I did. I have a sign error. It's not W dot equals the sum of the M dot H's going out minus in. It is in minus out. In minus out. Oof. In minus out. Let's fix that. I'm going to actually put it in blue so it's really obvious where I'm changing things. And then this to be, thought something wasn't sitting right. H4 minus H5. Whew. All right. So let's fix that down at the bottom. H4 minus H5. 4 minus H5. All right. And now let's plug in some numbers. So I've got 0.371. It's kilograms per second. And now let's plug in those H4 and H5 numbers. So I have 2738.1, 2738, not 0.1, 0.6, minus 2336.69. This is in kilojoules per kilogram. But unfortunately, we do need it in terms of horsepower, I believe. And there is a unit conversion. Let's go look at what it is. Make sure this is the unit conversion that's actually on there. Yeah. So 1 horsepower, 0.74, 57 watts. 0.7457 kilowatts, and a kilowatt is a kilosecond. All right, so hopefully what we've got there, we've got a W dot, and that ends up giving us 199.9 horsepower. Perfect. All right. Hopefully that was helpful. Let me know if you have questions. Remember, the key is to just make sure you're specifying what control volume that you're looking at and apply your conservation of mass and your conservation of energy. And you're just doing that to different control volumes to relate the different components. All right. Hopefully that was helpful. Again, let me know if you have any questions. Thank you.